You've probably heard about it, right? That Python can't really use multiple CPU cores at the same time, all because of this thing called the GIL. For years, it's been called a bottleneck, a major roadblock to true performance. But here's the thing. Is it really the villain everyone makes it out to be? The story, it turns out, is way more complicated and a lot more interesting than you might think. So that brings us to the big question. Can Python achieve true parallelism? For decades, the simple and kind of frustrating answer was no. And it all came down to one single component, the global interpreter lock. To really get why it existed and, why it's finally changing, we have to go back and see how this whole thing started.
To understand the GIL, we really have to rewind the clock, way back. We're talking the early 90s, when computers were, let's be honest, a lot simpler, and the idea of having multiple cores in a processor was basically science fiction. Okay, first things first, we got to get two crucial terms straight: concurrency and parallelism. Think of concurrency like one chef in a kitchen, juggling a bunch of different recipes. They're chopping vegetables, then they're stirring a sauce, then they're checking the oven. Progress is being made on everything, but only one single action is happening at any given moment. Parallelism, on the other hand, well, that's like having multiple chefs, each in their own kitchen, all working on different dishes at the exact same time. That is true simultaneous power.
So the GIL, the global interpreter lock, is basically a rule in Python that says, hey, only one chef can cook at a time. That's it. Even if you've got a whole team of chefs ready and waiting, the GIL forces them all into a single file line. It's one single giant lock on the entire kitchen. But why? Why would this rule even exist? Well, it wasn't some mistake or an oversight. It was actually a really clever solution to a super critical problem. It was all about preventing total chaos in how Python manages its memory, specifically with a system called reference counting. See, in Python, every single object has this little counter, a reference count, that keeps track of how many variables are pointing to it. When that counter hits 0, poof, the object gets deleted. The GIL prevents something called a race condition, where two threads try to change that count at the exact same time, which could cause all sorts of problems, like memory leaks or even crashes. This simple lock made Python thread-safe, and it made integrating powerful C libraries an absolute breeze. And honestly, you can't overstate this. That one decision was absolutely crucial for Python's early success. So the GIL was a brilliant, pragmatic solution for the world it was built for. But then the hardware world didn't just change, it had a revolution. All of a sudden, computers started shipping with 2, then 4, then 8 or more cores. They were built from the ground up for true parallelism, for having all those chefs in all those kitchens. And just like that, Python's one thread at a time rule went from being this clever safeguard to a major performance bottleneck. And this really gets to the heart of the conflict. Our computers now have these massive, multi-lane superhighways for processing power, but the GIL was forcing all of Python's traffic down a single, one-lane country road. And here's where it gets really weird. I mean, truly counterintuitive. For tasks that are heavy on the CPU, using multiple threads in Python can actually be slower than just using one. No, that's not a typo. The constant fighting between the threads, all trying to grab that one single lock, creates so much background noise and overhead that it just wipes out any potential speedup you were hoping for. So, if the GIL was such a pain, how did Python not only survive, but become one of the most popular languages on the planet? Well, it's simple. Developers are smart. They found really clever ways to work around it. They basically used two main strategies. Multi-threading was still perfect for what we call I/O-bound tasks. So think about any time your code is just waiting for a file to download or for a database to send back a response. During those waiting periods, Python's GIL gets released, and that lets another thread jump in and run. It's not true parallelism, but for waiting games, it's super efficient. But for those really heavy CPU crunching tasks, developers turned to multiprocessing. And this is the key workaround. Instead of more threads, it creates entirely new, separate Python processes. Each process gets its own memory, its own interpreter, and, critically, its very own GIL. It just completely sidesteps the original problem, letting tasks run in true parallel on different CPU cores. And this led to a really simple rule of thumb, a mantra that's guided Python developers for years. If your code is doing a lot of waiting, use multithreading. But if your code is doing a lot of thinking, a lot of heavy computation, use multiprocessing. But look, these workarounds, especially multiprocessing, They add complexity, they add overhead. For decades, the community dreamed of a Python that was finally free from the GIL's constraints. Well, guess what? That future, it's finally arriving. The pressure to solve this problem came from everywhere, but especially from the worlds of AI, data science, and scientific computing. Fields where squeezing every last drop of performance out of a multi-core machine is absolutely critical. Having to rewrite huge chunks of code in another language like C++ just to escape the GEL was becoming a really painful chore for a lot of people. Now, this change didn't just happen overnight. It was the result of a decades-long journey, from the GIL's introduction back in the 90s through the challenges of the multi-core era, and it all culminated in 2023 with a landmark decision, accepting PEP 703, a massive, comprehensive plan to finally make the GIL optional. And that massive change officially arrived with the release of Python version 3.13. Now, here's how it works. The GIL hasn't been completely ripped out of Python. Instead, it's now optional. Developers can use a special flag when they build Python from source to create what's called a free threaded version. And in this version, all the complex machinery for thread-safe memory management happens without a global lock. Finally unlocking true multi-threaded parallelism for those heavy CPU-bound tasks, right inside Python itself. This is a monumental shift. It's a whole new era for Python. And it leaves us with one incredibly exciting question. With its most infamous limitation finally broken, what new frontiers will Python conquer next?